Hello everyone, this is Workshop 5, naming ionic compounds, molecular compounds, and acids. So each of these types of compounds are going to be comprised of different types of atoms, and because they have different compositions, we have different ways of naming them. We're going to go through how to name each separate type, break down all the steps, make it easier to digest, and then we'll go over a bunch of practice. We're going to start with our ionic compounds first. So anytime you hear ionic, you're going to be seeing a bond between a metal and a non-metal. Remember, your metals are going to be largely on the left side of the periodic table, while your non-metals are going to make up a smaller section on the right side of the periodic table. And so when we were looking at ionic compounds, the general formatting of the name is that you're going to have your cation, which is your metal. We call them cations because when the metal forms an ion, they are positively charged ions. So you just write out the name of the metal itself. You have a space, and then you write out the anion, which is going to be your non-metal. And just like cations are named because they form positive ions, anions are going to form negative ions. But you're going to replace the ending with IDE. Or if you want to rewrite this a little bit to not talk about cations and anions, you name your metal first, you have a space, and then you name your non-metal, and you change the non-metal's ending to IDE. To give an example, one of the most common ionic compounds is going to be NaCl. This is table salt. You have a metal, sodium, and you have a non-metal, chlorine. So we name our metal or our cation first, sodium. No changings to the ending, nothing else to add. And the next word is going to be, we are working with the chlorine atom, so chlor. But we're not going to put chlorine, we have to change the ending to chloride. So sodium, chloride. And that is the main format of ionic compounds. And now the main difference with this naming convention is going to be if you have a main group metal or a transition metal. If you're working with a main group element, then this would be the final name. Sodium is in group 1, and so we don't have to worry about the charge of sodium because the sodium ions are always going to have the same charge. If we broke down sodium chloride into its ions, sodium will always have a +1 charge, chlorine will always have a -1 charge in this compound. And any compound containing sodium, the sodium ions will have a +1 charge. It's a main group element. We don't have to have any notation to show its charge. But let's say now we're working with a compound that is not a main group metal. Let's say we're working with iron chloride instead. This way we just see, we can focus on the metal part of it and not necessarily the anion. So, two different compounds, FeCl2 and FeCl3. Iron itself, Fe, is a transition metal. It doesn't have a consistent charge like sodium would. And so in this case, we're going to follow mostly the same rules, but we have to actually pay attention to what the charge of iron is. Chlorine has a relatively constant charge of -1. I'm just going to move this one down real quick. CO3, there we go. Chlorine is more or less always going to be -1. There are rare circumstances where it won't be, but for our purposes right now, chlorine has a -1 charge to it. Since there's 2 chlorines, the overall charge of all of the chlorines is going to be -2 for this molecule. There's no charge on the compound itself, so we need our charges to balance out to equal 0. If there's 2 chlorines and both give us a -1 charge, we have -2 overall, and so to balance it out, we need +2 from the iron. And so in this case, we have iron. We're still going to name our metal first. And now the only thing we have to change is that we're going to put the charge of the metal in parentheses next to it. This is a +2 charge, so this is iron 2 chloride. Same thing with FeCl3. Chlorine has a charge of -1. There's 3 chlorines in this compound, so there's an overall charge of -3. And so to balance this out, iron needs to have a +3 charge. And so now instead of iron 2, it's iron 3 chloride. It's still metal first, then nonmetal, followed by IDE, or cation, then anion, followed by IDE. That rule itself does not change. The only difference is that if you have a main group element, you don't need to put, or a main group metal rather, in the first column or the second column. If you have any metal from those first 2 columns, you don't need to put the charge in parentheses because that is going to stay constant. No matter what compound that atom is used in, it's going to have a constant charge. Sodium always has a +1 charge. Potassium always has a +1 charge. Calcium will always have a +2 charge. The actual charge itself does not need to be denoted. But if you have a transition metal like iron, you have to state which version of iron you're working with. Depending on whatever iron is bound to, it could change its charge, as we see here with iron 2 chloride versus iron 3 chloride. It's almost the exact same compound, but because there's one additional chlorine, it changes the charge on the iron, and so we have to actually make a note of that when writing out our naming system. Other than paying attention to your Roman numerals and having your endings, those are the main rules for ionic compounds. And so now we're going to go into molecular. There's not too many rules when it comes to ionic compounds, but with molecular, there's a little bit more memorization involved. A lot of the memorization with ionic compounds is going to be coming down to how well you know the elements themselves. So identifying that Fe is iron, and just being able to associate chemical symbols with the names of compounds, or vice versa. The name of the atom itself with the chemical symbol. And then of course with ionic compounds there is a lot of, well, not a lot of math, but some level of math involved to make sure that your charges are balanced out. Because if your charges are properly balanced, then you know you have the correct compound. But now with molecular compounds it gets a little bit trickier. Because if ionic was metal and non-metal, we're looking at that transfer of electrons, and we can use the charges to write out the name. We don't need to denote how many of each element there is in the compound because the charge tells us immediately. If we had been given the name iron 2 chloride, we'd still be able to get this formula without the number of each atom being given to us, because if we know the iron has a +2 charge and chlorine usually has a -1 charge, we could figure out by essentially doing the reverse of what we did here to get the proper formula. With molecular compounds, though, we don't have the ability to use their charges to figure out compound from name or name from compound. Because in molecular compounds, you are bonding 2 nonmetals. And when you have 2 nonmetals bound together, you are not transferring your electrons, you are not creating ions, you are sharing your electrons. And because you are sharing the electrons, the way that the electron density works makes it more complicated to know what the actual charge on your compound is. The overall compound still has to reach neutral, but you can't use the same logic that we use here because you're not necessarily making the full ion that we are with ionic compounds. So instead, we need to keep track of prefixes. We're going to say in the name of the compound just how many of each atom that we have based on the prefix we give the element. And so to follow the general naming order, you're going to have a prefix attached to prefix plus first nonmetal, just whichever one appears first in the order. Space, and then another prefix plus second nonmetal, And again, we have that IDE ending on the second half of the compound. So it was cation, then anion with the IDE ending, or metal, then non-metal with the IDE ending. The same thing happens with molecular compounds. It's just instead of having metal, non-metal, it's first non-metal, second non-metal with the IDE ending. It's still the same order. And now for our prefixes, we need to write those out. So we're only going to go up to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. A lot of these are going to be familiar if you are comfortable with geometry, or at least remember a lot of the names of the shapes that are associated with these numbers. It's really 1 through 4 that don't follow that same numbering system. So if you have 1 of an element, you're going to like prefix it with mono. 2 will be di. 3 is tri. 4 is tetra. And then from 5 onwards, it follows the same prefixes that you would assign to shapes that have the same number of sides. So 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. So to give more examples, I like using the nitric oxide family as examples because there's so many different combinations of nitrogen and oxygen. So let's say we have NO versus N2O versus NO2. All different ways to bind nitrogen and oxygen together. All of these are valid compounds. These are all molecular compounds sharing their electrons differently with each other. And so because there's no consistent way to make the charges balance out like we will with an ionic compound, we have to use our molecular naming system. If your first element does not have a subscript, if it's just one of them, you don't need to put mono. So we're not going to put mononitrogen. We are just going to put nitrogen for this first one. But the second word always has to have a prefix on it. So it's nitrogen, there's 1 oxygen, so nitrogen monoxide. Now here we have N2O, our first element has a subscript, so now we do have to put a prefix on it. So 2 nitrogen, dinitrogen. We have 1 oxygen again, so it's once again monoxide. Last one, we have 1 nitrogen, but it's our first element, so no prefix, just nitrogen. And now we have 2 oxygen, so it's nitrogen dioxide. Remember that second element always getting that suffix of IDE. So, ionic compounds, metal plus non-metal. Non-metal ends with the IDE ending. It's based off of charges. We are transferring electrons, and so if your metal is a main group metal, you don't need to denote its charge. It is assumed from the name itself. Sodium has that constant charge, don't need parentheses. If it's a transition metal, you need to denote the charge in the name of the compound. If you don't denote the charge, you have no way of knowing exactly which form of iron chloride this is. For molecular, it's a transfer, it's a sharing of electrons. We can't use charges for the naming, so instead we use prefixes to say exactly how many of each element there are. Nitrogen monoxide, dinitrogen monoxide, nitrogen dioxide. And to actually give just one more, N2O5. We have 2 nitrogens, so dinitrogen. We have 5 oxygens, so pentaoxide. I will say I've seen pentaoxide and I've seen pentoxide dropping the A. Both should be correct. I would just, if anything, ask your professor to see if there's a way that they prefer it. But I have seen both pentaoxide and pentoxide. So either should be acceptable. But now that we have ionic and molecular, the last one is now our acids. I'm going to erase the ionic information. There we go. So now we have acids. So acids are going to be a little bit similar to molecular in a sense. We're still not really going to be working with metals when looking at acids, but the main thing is that it must contain a hydrogen, minimum one hydrogen. It could have more than one, but at least one hydrogen and a non-metal. Okay, similar to a molecular, non-metal and non-metal, but now it's a hydrogen and a non-metal. And now, ionic compounds, we have two different naming systems of the main group naming and the transition metal naming. Acids are going to have two ways of naming them, either binary acids or polyatomic acids or oxyacids. So to go over binary acids, binary acids are only going to contain two elements. The hydrogen itself bound to some element that I'm just going to label Z. This is going to be just some element on its own. Common examples, HCl, HBr, HI. Let me write this a little bit. HI. Hydrogen and an element, hydrogen and an element, hydrogen and an element. Specifically a non-metal. So when you're naming binary acids, I'll put it over here. Because it's binary, you're going to start it with hydro. Plus non-metal. And now similar to how we were ending the non-metal with IDE, we are going to end it with the suffix ic, IC. And the last part is that you're just going to stick the word acid on the end of it. And so HCl would be hydro. It's chlorine, so chlor, but instead of chlorine, we're going to put chloric. I'm a little bit out of space over underneath. Acid. HBr, hydro, bromine, but instead of bromine, it's going to be bromic acid. And the last one, hydro. Iodine would be iodic acid. Binary acids, hydro for the hydrogen, the beginning of your non-metal, and instead of IDE, it's going to end with IC. And now, the other ones are oxyacids. Actually, before I write it, oxyacids are going to be a little bit different because it's going to involve our polyatomic ions. But first, let's go over all of the polyatomic ions that we know. These are the polyatomic ions that are listed in your textbook, with the ones starred being the ones that are in the packet that we are working with. I'll be honest, it is a lot of compounds. It's going to look a little overwhelming, but break it down step by step, look at a few of them each day, get used to the commonalities in all of them. These are the polyatomic ions that are in your textbook. The ones that are starred are the ones that are written currently on the sheet that we are working with. It does look like a lot. There are a lot of polyatomic ions that have to be known, but just remember you have time to study these. Take a few of them each day, get used to memorizing them, write them down a bunch, use flashcards, and eventually you'll get very comfortable with all of these. If you are currently in the lab, then you're going to get extra comfortable with these because quite a few of these polyatomic ions pop up in the chemicals that you're using. And so it's just, you also get that additional practice of just seeing them and using them constantly. But you'll notice a lot of them have a prefix that tells you what element you are working with. Not for all of them, but for stuff like nitrate and nitrite, that uses nitrogen. Carbonate uses carbon. Chromate is going to use chromium. The chlorites and chlorates are going to use chlorine, so on and so forth. Now, once you have these polyatomic ions down, or as you're working on some homework, if you have your notes with you, these are going to be important when naming ionic compounds and when naming our acids, of course. You're not going to see polyatomic ions pop up in non-metal and non-metal. They're not going to really appear in molecular compounds because these polyatomic ions, as you can see, all have some type of charge associated with them. You'll also have to have the charges of all of them memorized. They have a charge associated with them. They are ions. They are going to form those metal and non-metal bonds, or they're going to form an acid which breaks down into ions when put in water. When it comes to ionic compounds, the rules themselves don't change except you ignore the IDE rule. We saw before, I don't have much space, but we saw before with NaCl that this becomes sodium chloride because chlorine is our non-metal. We have to put the ID ending on the end of it, the suffix. Let's say we bind sodium with a polyatomic ion. Sodium nitrate would be NaNO3, and that's exactly how you would write it. Sodium stays sodium, and nitrate stays nitrate. And that's going to be true with all of the polyatomic ions. If it was sodium sulfate, it would just be written sodium sulfate. If I bond sodium with chlorite, it'd be sodium chlorite. So when you have a polyatomic ion in an ionic compound, the naming rules don't change. It's still metal, then non-metal, the metal and the polyatomic ion, but you have one less rule to worry about. You just write it as you see it. And the parentheses, the Roman numerals, are still going to apply if you have a transition metal. We saw iron 2 chloride was different than iron 3 chloride. And same applies with polyatomic ions. I'm actually going to change that to ClO3. Same thing, we have to know what our charges are. ClO3, chlorate, has a -1 charge. There's a 2 here, so there's 2 moles of chlorate. If there's 2 moles of chlorate, that means there's an overall charge of -2. So this iron has to be +2. This is iron 2 chlorate. The rules themselves aren't changing. It's still metal and then non-metal. But now you don't have to worry about the suffix. The only thing you should worry about is making sure you write the name in the correct order. And if it's a transition metal, putting that charge in Roman numerals. Now, when it comes to acids, it's going to be a little bit different. We saw with binary acids, we had hydrochloric acid, hydrobromic acid. You have to put the word hydro for the hydrogen. You have to end your non-metal with IC, and you have to put the word acid at the end of it. When it comes to oxyacids, acids with a polyatomic ion in it, you do not have to put the word hydro. You are not going to put the word hydro. The beginning, the prefix hydro is not going to be included in this. And so if I write HNO3, we have our polyatomic ion, our non-metal, and we have our hydrogen. That tells us it's an acid. Because this is a polyatomic ion, I'm not going to start this with hydro. I'm just going to go straight into the name of NO3. It's nitrate, and so it's going to become nitric. And you're still going to end it off with acid. That does not change. Versus now if I have HNO2, non-metal, hydrogen in front. Once again, it's nitrite now, so we're still starting with the beginning of the word, nitra. but now we have less oxygens, and so it's nitrous. Okay, the other color. Nitrous acid. And so to make this a rule that can be applied to all oxyacids, if your ion ends with ITE, you replace it with OUS when naming the acid. If your ion ends with ATE, it ends with ic. Hence why this one here, nitrate versus nitrite, nitric acid versus nitrous acid. And so that's going to make memorizing these ions even more important. You have to know what the ending is to know the correct way to name your acid. If you have HNO2, you can't call it nitric acid. That is a completely different acid. And to demonstrate that, when knowing the properties of these two acids, even though they're only different by one oxygen, nitric acid is a strong acid. It is highly corrosive. Nitrous acid is a weak acid. It's still acidic, it still has corrosive properties, but it is much weaker than nitric acid is. One is strong while one is weak. The naming is a very, the names create a very distinct difference between the two to be able to differentiate what you're actually using each for. Because if you don't know the difference between the two, you can cause a reaction to go very poorly. And so now that we have our naming rules for ionic compounds, our molecular compounds, and the different types of acids, let's go into some practice problems. These are the first 12 problems of the first part of the practice questions. They want us to take a formula and write it out in its written name. So first things first, when looking at a compound, always see, is it an ionic compound, molecular compound, or an acid? We have Cu, which is a metal, and we have ClO3, a polyatomic ion, which acts as a non-metal, and so this is ionic. This is ionic. We know we have to name metal, then non-metal. Cu is going to be copper. And now, before you write the rest of the name, see where on the periodic table copper falls. Copper is a transition metal, so we know we're going to have to put the charge in parentheses. Since it's a polyatomic ion, when naming our nonmetal, we don't have to include the IDE suffix. It's just copper, charge, and then chromate. Oh, sorry, wrong compound. Cl, chlorate. Now the last thing to do is figure out the charge. From our list of polyatomic ions, chlorate, all of the chlorine series of polyatomic ions have a charge of -1. If this equals to 0, and we only have one copper to balance it out, this copper must have a charge of +1. So this is copper 1 chlorate. Next compound, we have oxygen, which is a nonmetal, and fluorine, which is also a nonmetal. So we have a molecular compound. If we have a molecular compound, we know then we have to think about our prefixes. Oxygen has no subscript. There's only one oxygen, so we don't need to include a prefix. So this is just oxygen. And now F, fluorine, there are 2 fluorines, and so we need to put the prefix for 2. This is di-fluor. Fluorine is not a polyatomic ion. We have to include the change of suffix. This is not oxygen difluorine, it is oxygen difluoride. Next one, MnOH2. So Mn, that's going to be a metal. OH is a polyatomic ion, it's going to be a non-metal. So metal and non-metal, we have an ionic compound. Mn is going to be manganese. Manganese is, again, a transition metal, so we have to put parentheses for a charge. Polyatomic ion, we don't have to change the ending of it, we just have to know the name of the ion. OH is hydroxide. Now we have to try to balance out the charges. One group of hydroxide would have a -1 charge. The subscript 2 outside of the parentheses tells us that we have 2 moles of hydroxide in this compound. So that means the overall charge of all of the hydroxide is -2. We need the charges to balance out to 0. And so if it's -2 here, the only way to balance it out to make it neutral is to have manganese have a +2 charge. So it's manganese 2 hydroxide. 4, KClO4. K is a metal. ClO4 is one of our polyatomic ions. It's going to be a non-metal, so we have an ionic compound. K is potassium. And potassium is a main group metal. It's in the first column, so we don't have to put parentheses. ClO4, polyatomic ion, we don't have to worry about changing the suffix, so we just write the name of that compound. ClO3 is chlorate, ClO4 is perchlorate. So this is potassium perchlorate. H2CO3, we have our compound starting with a hydrogen, or multiple hydrogens, but still starting with hydrogen, and a polyatomic ion, which would be a non-metal. Hydrogen plus non-metal, this is an acid. The non-metal is a polyatomic ion, it's an oxyacid, so we don't have hydro to start our naming. And so we just have to know what compound this is. CO3, that is carbonate, it ends with ATE, so this is going to be carbonic acid. Al2O3. Al is a metal, O is a non-metal, and so we have an ionic compound. Al is aluminum. And now aluminum, while not part of those first 2 columns, does have a constant charge. Aluminum is one of the metals further to the right of the periodic table that you have to have the charge memorized of. Aluminum will always have a +3 charge, and so we don't denote the charge in our naming system. Even if it's not in one of the first 2 groups, aluminum always having a constant charge means we don't have to include it in our naming. So it just stays as aluminum, no parentheses. O is oxygen, so it's ox, and instead of oxygen, it has to end with that suffix I. So aluminum oxide. Even though we have 3 oxygens, it's an ionic compound, and so we don't have to put a prefix here. The charges of each element will tell you how to balance out the formula if you were to write it in the opposite direction. SO2, S is a nonmetal, O is also a nonmetal, so this is a molecular compound. We have to think about our prefixes. S is by itself, it doesn't have a subscript, so there's just 1. We don't have to put a prefix. And S is sulfur. O is oxygen. It has a 2 subscript next to it, and so we have to put the prefix for 2. Sulfur di ox, and changing that ending to ide. Sulfur dioxide. HBr, we have a hydrogen and a non-metal, so we're naming an acid. This is an element by itself, it's not a polyatomic ion, and so it is a binary acid. Anytime we have a binary acid, we start our naming with hydro, then we name the element it's attached to, so bromine, so hydro, bro. Since it's an acid, it ends with the ending IC, hydrobromic acid. NH42, SO4. This one is definitely one of the trickiest ones to look at and relies a lot on your knowledge of polyatomic ions. NH4 is a polyatomic ion, and SO4 is a polyatomic ion. And in this case, the NH4 is acting as a metal because since these are both ions, sorry for the cut, there was a little bit of an issue with my recording. Anyway, back to number 9. So this one's going to be the trickiest when it comes to naming, or one of the trickiest, because you have to be very comfortable with your polyatomic ions. NH4 is a polyatomic ion, and SO4 is a polyatomic ion. Since they are both ions, and if you remember your charges, NH4 is positively charged, +1, while SO4 is a charge of -2, this is an ionic compound. You have a positive ion and a negative ion, a cation and an anion to make your compound. And so now it's just knowing the names of both. NH4 is ammonium, and SO4 is sulfate. No changing in suffixes, no changing in prefixes. It's an ionic compound with both parts having constant charges. Number 10, P4O6. We have a nonmetal and a nonmetal, so we have to know our prefixes. P is going to be phosphorus. It has a subscript, so we do have to put a prefix on our first element. 4 has the prefix of tetra, so tetra phosphorus. Still not changing the ending because it's our first element. We don't change the suffix of our first element. 6, the prefix is hexa, and we're working with oxide. So tetraphosphorus, hexa, ox, change of the ending, I-D-E. Tetraphosphorus hexa oxide. Or again, I've seen both hexa oxide and hexoxide, so that's likely more of just a preference thing. NiBr3, Ni is a metal, Br is a nonmetal. We are working with an ionic compound. If we're working with an ionic compound, we name our metal first. Ni is nickel. Nickel is a transition metal, so we need parentheses for our charge. Br is bromine, and since it is our anion, it becomes bromide. Now we have to know the charges of these elements, specifically the bromine. Bromine is a halogen. It's going to have a -1 charge for one of them, and since there are 3 bromines, it's going to have an overall net charge of -3. If we want this -3 to be balanced out to equal 0, our nickel must have a charge of +3. So nickel 3 bromide. Last one, Si4H5. This one's also a little bit more difficult because Si is going to be one of your metalloids. When it comes to naming conventions, metalloids tend to follow the non-metal naming convention. So we're going to treat it as a non-metal with a non-metal. And while hydrogen is here, hydrogen is not leading the compound, and so we're not going to treat it as an acid. Hydrogen has to be in the front of your compound. So Si4H5 are 2 non-metals. So we need our prefixes. We have 4 Si, so it's tetra. Si is silicon. I forget if it has an E at the end or not, so I'm just going to leave it like this. So tetrasilicon. We have 5, so that is penta. Now we are used to naming hydrogen as hydro for our acids. Since it is now the second element in our compound, we're still going to end it with that IDE suffix. So instead of hydrogen, we have hydride. Tetrasilicon pentahydride. So this first set was taking formulas and writing out their full names. The next set of problems now gives us written out names, and we have to now write the formula based on the name they've given to us. So these are again the first roughly 12. I dared to skip 1 or 2 of them just because we had gone over them either in the last section or I used one of them as an example when first going over the rules. Let's start with this first one, lead to carbonate. So lead is a metal, carbonate, polyatomic ion. So this is going to be an ionic compound. And so now we have to know the chemical symbols from the names. Lead is Pb. and carbonate is CO3. Now we have to pay attention to the charge. It's lead 2, so lead has a +2 charge, and the charge of carbonate is -2, and so these two elements are already balanced. It's just going to be PbCO3, no subscripts on anything. Now we have iron 2 phosphate, so again, metal and a polyatomic ion, so a non-metal. Iron symbol is Fe, phosphate is PO4, and now again we have to know the charges. Iron, they're saying, is +2, but phosphate has a charge of -3. And so we have to somehow get these equal to 0 using subscripts to balance out the formula itself. And the quickest way to do this is to cross multiply. If we multiply phosphate by 2 and iron by 3. So iron 3 and phosphate 2, remember, since it's a polyatomic ion, it has to go in parentheses. You're not going to put PO8, you're going to put parentheses PO4 parentheses 2. Because now if you have 2 phosphates, and each of them is -3, we get -6 from both of them. And if we have 3 irons and all 3 of them are +2, we get +6 from all of the iron. And it balances out to 0. And so with iron being +2, phosphate being -3, our formula is Fe3PO4 2. Tetrasulfur decaoxide, we're working with prefixes, so we know it's a molecular compound. And so we're going to look past our prefixes to see what our elements are. So tetrasulfur, sulfur has the chemical symbol of S. Tetra tells us 4. Oxide is oxygen. Deca tells us 10. S4O10. Magnesium carbonate. Magnesium is a metal, carbonate a non-metal, it's a polyatomic ion. Magnesium symbol is Mg. And now magnesium is one of our main group elements, hence why it doesn't have Roman numerals written in the name. And carbonate, we wrote before, is CO3. Once again, we have to make sure the charges are balanced. Magnesium has a charge of +2 always, and carbonate has a charge of -2. And so, once again, this is balanced, and just like the lead carbonate, there is no subscripts for either of these, or additional subscripts for either of these components. Titanium 4 chloride, so we're working with a metal and a non-metal. Titanium symbol is Ti. Chloride is chlorine, so TiCl. And now we worry about our charges. Titanium, they're telling us, has a charge of 4 based on the Roman numerals, so +4. And 1 chlorine only has a charge of -1. We need this to somehow equal 0, so again, we're going to cross multiply our numbers. Put the 4 on the chlorine and the 1 on the titanium. If we have 1 titanium, its +4 charge is just going to stay +4. If we have 4 chlorines and all of them are contributing -1, that is -4 overall, and that balances out to 0. Actually, let me put this back here as well, just to leave it. In this one as well. So 8 ammonium hydroxide. These are both polyatomic ions, and so knowing the structure for both of these, ammonium is NH4. Where are my dashes? There. Ammonium is NH4. Hydroxide is OH. Knowing the charge of both of them, ammonium has a +1 charge, hydroxide has a -1 charge. Both of them are already balanced, and so it's NH4OH. Potassium chromate, we have a metal and AZ ending, so we have a polyatomic ion. Potassium, no Roman numerals, main group element. Potassium symbol is K. Chromate, chrome tells us there's going to be chromium in this polyatomic ion. Cr, it's just regular chromate, not dichromate, so it's CrO4. And now checking our charges, potassium will always have a charge of +1. Oh, that looked like an H. +1. But chromate has a charge of -2. And so because chromate has a charge of -2, we need these to balance. We cross multiply our numbers. We're going to have K2CrO4. The +1 from 1 potassium means there will be a +2 from 2 potassium to balance out the -2 from the chromate. Diphosphorus heptaselenide. We have prefixes. We know it's a molecular compound, and so we follow our prefixes to know how many of each element we have. Diphosphorus means that we're starting with P. Di meaning 2. Heptaselenide, so we are working with selenium, which is Se. Hepta is 7. So P2Se7. Perchloric acid, acid telling us we're going to have hydrogen, so we could already start this compound off with an H. There we go. And now we look at the naming. There's no hydro in it, so we know it's going to be a polyatomic ion, not a standalone element. Perchloric, the chlor tells us that there is chlorine in this compound, so we know it's going to be something in the ClO family. ICE ending tells us it's either going to be ClO3 or ClO4. Because it's perchloric, that means it is perchlorate, so HClO4. All of the chlorine, the entire chlorine family of oxyacids have a charge of -1, and so this is balanced. Manganese oxide, metal and nonmetal. Roman numerals telling us that it is a transition metal, and we have to look at our charges. Manganese symbol is Mn, and oxide is oxygen. Now, this is telling us that manganese has a charge of +4. Based on where oxygen is on the periodic table, it has a charge of -2. And so in this case, we can cross multiply. And so we would have Mn2O4, but both of these are divisible by 2. If both the numbers that you have, both of your subscripts, are divisible by some factor, you are going to divide those by said factor. So if 2 and 4 are both divisible by 2, then Mn2O4, after cross multiplying, becomes just MnO2. And that works because this would have a charge of +4. -2 times 2 would be -4, and those cancel out. Diiodide heptanitride, we got prefixes, so it's a molecular compound. Iodide, we're working with iodine. Di meaning 2. Nitride, nitrogen, we're working with nitrogen. I spelled it wrong, it's not hepa, it's hepta. Sorry. Hepta, nitride, hepta meaning 7. I2N7. And now last one, nickel 2 phosphate. We have a metal and a non-metal. It is a polyatomic ion with the ATE ending. And so nickel symbol is Ni, phosphate is PO4, and now we just need to look at our charges. Nickel has a charge of +2 based on the name. Phosphate always has a charge of -3. And so similar to iron 2 phosphate, we are going to cross multiply these, putting our polyatomic ion in parentheses when adding our subscript. So cross the 2 and the 3, Ni3, PO4, 2. 3 times 2 is +6, 2 times -3 is -6, +6 and -6 will cancel out. And so just like we were able to go from a formula to a name, we can also use the name to then get to the formula. When going from name to formula, math is often a lot more important because oftentimes you're not going to know the actual charge of your ionic compounds and your acids. You have to actually make sure that everything is balanced before you finish writing it. Because if we took magnesium, that's a bad example, if we took potassium chromate and left it as just KCrO4, that would not be correct. Potassium chromate is specifically K2CrO4, and we don't have to worry about putting charges in the name, and we don't put prefixes in the name because we know that when their charges are balanced, we only get the one compound. It's not like our molecular compounds where you have to use prefixes because there's so many different forms of the same skeletal structure. That is the end of this workshop. If there are still any questions on the content that was covered in this recording, absolutely reach out to the Math and Science Resource Center here at John Jay to get more assistance. You can book an appointment yourself through John Jay Navigate, or you can go to the Tutoring Center on campus, room 1.94 in the new building, and someone at the front desk can help you book an appointment. You can book one-on-ones either in person or virtually, and there are plenty of tutors here who can help you understand the content better.